Right. Welcome to the third session of these festivities. I'm introducing Rupak Majumdar. He's like Andreas, he's coming out of MPI, Max Planck Institute. He's still there as a scientific director. He's like Andreas in the neat parts of Germany, I would say. Like he's in Kaiserslautern, kind of close. Also, I've seen him at many PhD defenses, and so he helped bring people up like me, not my defense, but still. And I also have a colleague at Satora who worked with him, Jaroslav Bendik, and his interests are in verification of X, for X being very many things, and in automata theory.
Thank you. Well, thank you. It's a pleasure to come and talk here. And of course, Andreas and I have known each other for a very long time. I was an intern in Saarbrücken MPI at the end of my first year of PhD, and Andreas was, of course, there. And I think one of the discussions during that visit was a discussion with Tom Hensinger, how model checking and verification can never really work for software, right? I think you probably remember this. And then I was interning with Tom Ball and Sriram at Microsoft, and Andreas came for a visit that Tom talked about. But then, about a year later, I was at LIX in Boston, and I was kind of a beginning graduate student, and I think what was extremely special for me was that Andreas and actually Shankar came and had a discussion with me as equals. We were all discussing what's the next thing for the, the important problems of the thing. And that was really a very nice turning point for me as a young graduate student to be taken seriously by, famous people. And since then, of course, Andreas and I have had many discussions about many different things. And the talk that I'm going to give today is about some work that I've been doing over the last couple of years at Amazon with a bunch of people that's working on roughly software verification. And I want to start by saying that, well, there's all this work going on in sequential verification of software, including the things like SLAM and so on that we talked about. And the natural question is, what's going on with the verification of distributed systems? And to be honest, distributed systems are really where the money in software is being made, right? So if you think about Amazon, well, it's a very big distributed system with many, many different services. And the question is, these systems are complex, they fail in very unpredictable way. What tool support can we give to people who are working in this area, right? So who are building these systems. And in this context, I remember that there was a very early meeting about software verification at SRI. I think, Shankar, you organized this Grand Challenge workshop. And there, Amir Pnueli had this thing that, well, as far as model checking was concerned, well, hardware was a distraction. Software was where we wanted to get to. And I think what I would like to tell you here is that sequential software was a distraction. We should really get to distributed software. Okay. Now that we have solved all problems there. Yes. Okay. So now to the more technical part, well, I'll talk about the MUST project, which is something that we have been working on at AWS with many people who are also in this room and others. And the goal of this project is essentially to see what it takes to look at distributed system implementations and be able to reason formally about these implementations, right? So what are the kind of systems? Well, at the core of many of those services that I showed you are some very core distributed algorithms. For example, there is something called a distributed replicated log, where essentially you have a number of clients who can send write or read requests, and you want to make sure that each reader of this log essentially reads what has been written in exactly the same order. Okay, so if it's a sequential object, then this is very easy to do. It's kind of a shared register, if you wish, or a shared vector or a queue, right? So whenever a write request comes in, you insert it on the queue. The read request kind of reads the queue left to right. But the trouble is that if you have a distributed system where these clients are coming in and you have to somehow make sure that this whole thing is fault tolerant, this becomes a rather complicated piece of software. And you have to make sure that, you know, even when some of these internal nodes of this replicated log goes away, the clients still have a consistent view of this service. Okay. Of course, if you can build a primitive like this, then you can, for the most part, ignore many of the core distributed systems and build a lot of things on top. Okay. And this is indeed so, right? So, you know, you have some core primitives like Paxos, you have replicated logs and so on. And this allows many of these very large-scale systems to scale without everybody having to talk about every possible asynchrony in the network and every possible fault in the server. So you can think of these as abstractions that are very important. And the goal is, how can we reason about these core systems that provide these abstractions? Okay? And just as an example, here's how a replicated log protocol might work. You may put a bunch of servers kind of in a chain. You have some coordinator that for the moment we can ignore. It's there for fault recovery. And when a client comes and writes a request, you kind of write each node in this network writes to its own log and then forwards a message. And so it kind of goes to the tail. And once it gets written on the tail, then it sends an ACK to the client saying that, yes, this write has been done. And then when a client comes and does a read request, it goes directly to the tail and tells you the value that's written, right? And with a bit of thought, you can figure out that this is a very consistent view of a replicated log. And the harder part is that, well, you have to make sure that this replicated log works as advertised, even when certain nodes fail. And this, again, is something that you can do by the coordinator by setting up new links and making sure that this additional data is forwarded and so on. Okay. So these are the kinds of systems that we would like to verify. Okay. And of course, you know, you can get the algorithmic description that if you have a protocol like this and with k nodes in this chain, then it can tolerate k-1 faults. But of course, when you look at the implementation, there are many, many other issues that makes writing these systems very difficult, right? So the algorithm or chain replication probably fits into half a slide. The implementation that you would actually deploy is probably many thousands of lines of code. And those thousands of lines of code are there for good reason. Okay, so how do you gain confidence in your implementation? And this is where this MUST project comes in, and it's part of a much bigger picture of, you know, how do we reason about concurrency and distributed systems. But I will just focus on a tiny piece of it that we have been building, and this is essentially allowing model checking to work directly at the implementation level of these distributed systems. Okay. So MUST essentially consists of, well, you know, there is a modeling library. And you can think of this modeling library as an embedded domain-specific language sitting inside Rust. Well, why Rust? Because, well, there's a lot of interest in writing many of these core protocols that have to be very performant in Rust using the type system. And, well, in general, what MUST allows us to do is to take some of these nice things about the Rust type system to be able to do some checks that would have been quite difficult to do otherwise. So it's a modeling library for message passing that's embedded in Rust. It gives a generic partial order semantics of these message passing programs. I'll get to that in a second. And then it builds a lot of abstractions on top of a very core language. Right? So to the programmer, there is not really much difference. You know, they're using TCP listeners, they're using RPC calls and so on. But internally, the semantics of MUST makes sure that all of these things are understood in terms of the sends and the receives that MUST provides. The second part is a model checker. I will talk a little bit about the algorithms that go inside this model checker. And the third part is more, you know, somewhat of a higher level discussion of many of the things that I learned in trying to take an academic idea and trying to see how it turns out in the real world. Right? Okay, let's just focus on the first part. As I said, so a must model is essentially a normal Rust program using certain special API calls. And what are these API calls? Well, if you're trying to model a distributed system, you have to have some way of modeling the processes. You have to have some way of saying what these messages are. You have to specify the communication. And as many of you know, if you want to have a language that is somewhat that can abstract away from all the details of an implementation, you have to have some way of giving non-determinism, right? And so the very core must library is really very small. It gives you a way to spawn a process. It gives you a way of sending messages and receiving messages. So you know, as a process, you can send a message to another one. As a process, you can wait and receive a message from another one. And then you can have a non-deterministic choice baked into the modeling language. And then you have some kind of an assume that says, well, execute up to a certain point, check that a certain condition holds. If this condition does not hold, pretend that this execution never even happened. Okay? And roughly, these are the 4 core primitives, right? So this is the core language on which you build your semantics. Everything else is abstractions built on top. And the semantics that we give is directly as partial orders that you can get out of this execution. We call these execution graphs because this notion kind of came out of the weak memory semantics, and then more recently in the sort of looking at shared memory DPOR algorithms. And the idea is that you have some kind of sequential computation that's going on in each process that you have spawned. And then there are causal links between the send events and the receive events. Okay? And the particular set of causal links that you're allowed to have is given by something called a consistency model. And the consistency model just tells you, when you have a receive, what are the messages in this graph that can actually flow into it. Okay? And you see that this consistency model may be different for every kind of model that you have. For example, a TCP send may have a different semantics than a completely asynchronous send, right? So if there is a TCP send, then if there are 2 sends here, then this one must be received before the next one. But if it's a completely asynchronous network, this ordering may be changed. Okay? So I lied a little bit by saying there's only one send and only one receive. Essentially, for each of these kind of core semantic notions, you would have to have some, a corresponding notion of a send and a corresponding notion of a receive. And then the consistency model will tell you what causal links you can have in this graph. Okay, so this is roughly the core modeling language of must. And this is surprisingly versatile. You can do a lot of things with this. And the must model checker itself is a stateless exploration engine, which does very aggressive partial order reduction. Okay? And this partial order reduction is computed directly on these execution graphs. And what is quite important is that the model checker kind of knows many of the abstractions that we do on top of this very basic set of primitives. And by teaching the model checker these abstraction tricks, we can actually scale much better than if the model checker had no idea what is going on, right? So we can talk offline about specific examples. So the DPOR algorithm, again, is it's kind of a variant of a classic DPOR, dynamic partial order reduction algorithm. It kind of executes the program, and as it executes the program, it constructs this graph on the side. And then once it has finished one execution, it looks at these causal links and figures out which ones you can flip to give another consistent execution. And it keeps doing this until there are no more executions. Right? So I will just skip the particular details, except for to say that, well, the algorithm that we have guarantees 3 properties. First is completeness. So if you have a program, then this musts algorithm is guaranteed to exhaustively look at every non-isomorphic execution graph. And it's optimal in the sense that each of these graphs is looked at exactly once. And the point is that you do this with only polynomial memory overhead over the memory overhead of the program. Right? So getting all of these three things together is slightly complicated, but this is where the core idea of the model checker lives. Okay. So for example, this kind of partial order reduction is extremely important, even if, when you look at these kinds of protocols. For example, in this chain replication protocol, if you don't have any faults, then the number of executions that you need to look at is independent of the length of the chain, right? So if you have a number of concurrent write requests, then the number of executions that DPOR will look at is essentially k factorial, which corresponds to the order in which the clients put the writes into the log. But the length of the chain is actually irrelevant. Okay? And this is certainly not so if you did not have partial order reduction. Okay? So for example, if you just had 2 writes, well, these are the 2 message sequence charts that you get, and already you see that there are 212 sort of traces of executions that you can get, and in general, there's a very large number of executions. I will skip over how we deal with the sort of lower, how we build abstractions on top of these specific abstraction core primitives, and go directly to say that, well, we have applied the model checker to a number of things that you would expect. I don't want to bore you with the numbers, but the point is that this very aggressive partial order reduction allows us to finish exhaustively exploring systems for which, without doing any of these reductions, we cannot finish. Right? So there is certain things to be said about being able to exhaustively explore even a small number of requests on a complicated implementation of a distributed system.
What do you mean by aggressive?
Aggressive, well, okay, this is, I don't know. Let me say that it's optimal, right? So, yeah. And it's aggressive in the sense that, we give the semantics directly in terms of the execution graphs, right? So we are never even, thinking in terms of these traces. And just by thinking about these execution graphs as the representations, you can get this kind of an, optimal DPOR with small memory overhead, right? So. Okay. I will talk just a little bit about, going from this first part, which is all very nice and scientific and clean, to what happens if you try to make it into a product, right? So the first thing that I realized is that, whatever new and complicated verification technique that you introduce, it has to really fit into the way the developers are doing their work, right? So if the developers have to change their work in very complicated ways, there's an additional inertia, right? So I think a lot of the work that went into taking this core algorithm that was written in a few months into making it into something that an engineer who has no exposure to formal methods can actually use. It's actually a very large amount of work, right? And along the way, you kind of realize that, well, just because there are many publications, it does not mean that, well, some problem is solved. You cannot hope to say that, well, we have this super cool technical idea, now change whatever you are doing and use this. And just the fact that, well, you think that you have a better technology, that it makes into a better product. Because I think that thinking about product is a very different skill set than thinking just about the core ideas that get into the product, right? And at this point, one of the things that I initially struggled with is this Byron's idea that, well, everything has to be sound, right? And initially it's very constraining, right? Because, if you're doing testing, as long as something runs, you are kind of happy, right? Because, well, look, my tool ran. Right? On the other hand, it's a bit embarrassing because, what you're doing in a pure testing tool is that, well, at the end of the day, you can say, I did a local random walk in the space of, space of random choices in a program. And the obvious answer is, so what? So you did this random walk. What can you say about the system, which probably has billions of behaviors, and you've picked, I don't know, 100 samples, right? So in some sense, thinking about this very constrained situation where your goal is to make sure it works on every possible behavior makes you think about optimizations that at the end may get you a better testing tool, right? So in some sense, just thinking about, well, I have this distributed system, but I have an equivalence relation and behaviors. And these equivalence classes are the interesting things that we need to explore. Not every possible trace is already something that can get you into a better testing product, if you wish. Right? It is quite possible that what we have done here is always going to be used in testing mode by the developers who are actually using it. On the other hand, just because we thought through all of these kind of corner cases to make it sound, it kind of gets you into a somewhat better product at the end, because at the end, the natural question is, well, you have invested in these testing tools and so on. What is your return on investment? And I think they're saying that, well, at least you get this kind of exhaustive approach at some level is a better sell than saying, well, I did some random exploration. But I don't know if you're going to anyway. But of course, the other thing that you realize, and this kind of wraps up this talk, is that it's ultimately about the people, right? So when you develop technology, in some sense, you also are working with the people who are going to be using the technology. And this is always, this kind of back and forth is probably a very rewarding way of understanding what ideas to pursue next. And this is true not just in kind of making, a tool into a product, but also in research by itself. After all, the kind of things that we work on in science are largely determined by the people we like and our communities that we have around us, and the discussions and the fun discussions that we have doing them. So coming back to Andreas, I think he and I have this one paper with Jochen that we had a lot of fun writing. And I think that we spent an enormous amount of time discussing how to call this paper, because we submitted it to POPL. And we thought that the paper was very elegant and clean. And I think this was taken against us because the reviewers very dismissively said, this is not really a POPL paper, you can call it a pearl. Now, for those of you who don't know, pearls were supposed to be this elegant pieces of scientific work that should show up in places like POPL. But in practice, pearls had a somewhat derogatory connotation to them. It was like the piece of dust that's getting in our sides, and let's just layer it over, right? And then I think Andreas had a lot of difficulty calling his own work a pearl. And eventually, I think we wrote to Andy Gordon, who was the chair, saying that, look, the reviewers insist that we call it a pearl. We are very, it's very difficult for us to call our own work a pearl. So I think the compromise was that we called compositional verification a pearl and somehow got away in the title. But going, about a year after this paper was published, I met Igor Walukiewicz, who is a man whose taste I very strongly admire. And Igor had some, a word of praise about this paper. He said, I read your paper. It just read like a paper from the 70s. And because I know Igor, I know that this was a phrase of highest praise, that he could give. And maybe this is going back to Andreas's work, like many of these papers that he's been worked on and he has written feel like they're from the 70s. And I say this not as, as a derogatory way, but I think it's really very elegant, very clean, and very readable. That's all I have to say. Thank you very much, and all the best.
Very quick question. I feel bad making you walk all the way here. When you say modeling, you don't mean that these are then the things that run in production or whatnot. I was a bit confused by that word.
So you should think of it as also the things that run. But the way of thinking about this is that when you start writing these distributed systems, you kind of use non-determinism as much as possible, right? You use this non-det and the assumes and so on to build the environment in which your code is running, right? And as you write more and more of the code, essentially what happens is that you have your actual messaging library, right? And think of this as a Rust trait, right? The Rust trait says, oh, here's a network trait that has a send and a receive and so on. So you can plug the must version in and out, right? So you just do conditional compilation to get something that the model checker understands and runs. And you could do conditional compilation to your actual RPC library, and that's the thing that actually can run in production, right? So of course, when you run in production, all these assumes and the non-debts go away with the actual things that you have in the environment. But the point is to have a very seamless transition between more abstract models where the state space is smaller and the actual implementation that runs.
So Rupak, there's something fishy about that sequential thing that you showed. What happens when the head fails?
So this is where I didn't talk about the coordinator. So the coordinator is essentially a Paxos cluster, and it's doing this kind of fault detection. When the head fails, essentially the coordinator will move, it will find a new head, which is the next person.
Yeah, but what about the writes that are pending in the head?
The writes that are pending in the head, you see the head fails, these writes have never been propagated to the tail, and a write only finishes when it's written at the tail. So some writes can be lost.
But how would the coordinator find out?
The coordinator has, there's a whole fault detection going on in the background, right? So you can think about the coordinator as, implementing a heartbeat or a fault detector and then doing a leader election to figure out who's the next leader, right? And the leader is always the head. So it is possible that there are some writes that never get acknowledged, right? And therefore they never show up in the replicated log. But this is true in a distributed system with message losses, right? So maybe the write didn't even show up to the head. Right? So the only thing is the consistency. If it gets written onto the tail, well, everybody will have a consistent view.
Hey, Rupak. It's been a while. So there was this system, what do we call it? P#, then it became Coyote.
Yeah.
How does it, I think Coyote was the latest version of this sort of stuff on the .NET side. How does Musk compare to that?
So I think any of these things you can do in any one of these things, right? So the language itself is a variable, the algorithm itself is a variable, but they're kind of independent variables, right? So one of our design decisions was to embed this whole thing into a language that can go all the way to production, right? And so this was part of our choice of using Rust, which of course brings to a lot of these things, because as soon as you get into Rust, well, what's your story about async and so on, which you can kind of abstract away if you're working in a nice, small language like P, right? On the other hand, then there's a gap between what you write and what you run. And this is you have to figure out where your tolerance lies, right?
Right, but my memory might be faulty, but I thought Coyote went to like C#.
Right, so the point is that, exactly, right? So if you think about the Coyote project, it again moved into this world where the code is actually C#. And it will again look at the send and receives as the primitives, and then build a model checker behind it, right? So in that spirit, you can think of Must as doing exactly the same thing, right? So there is a version, so there is some large systems code being written, there is a code abstraction, and then there's a model checker that explores the space of abstractions, right? So
you mentioned the paper on parameterized verification, but the number of clients is fixed.
yes, so this is stateless verification, right? So what we can take offline is, how can you take something like this and kind of go to a parameterized version, right? So now, and the main thing here is that the parameterization is the number of transactions that you run together, because in some sense, the length of the chain and so on, they're actually defined in the deployment, right? And it's usually 3, 5, I don't know, right? So that's not the hard part of the parameterization. The parameterization is, well, what happens if you have many clients writing to this thing at the same time? And well, okay, so one trick you can do is columnization, non-interference, and so on. So even with things like stateless model checking, you can actually go quite a bit far in doing unbounded proofs, right? But that's a separate talk.
And so if I may, I will add an anecdote, because you mentioned that we talked at LIX in Boston, and I remember this very well, because together with Sriram and Tom, we were working on what became this relative completeness of abstraction refinement. And I was stuck at one point, and I discussed it with you, and somehow you said, oh, this reminds me of an exercise of George Necula in the verification class. And we dug out that exercise, and there was the proof. I mean, the exercise was to prove a certain relationship between pre and post for deterministic updates. Do you remember this? And this saved me. Yeah. So thank you for this.
Since George is not here to defend his ideas, I will take credit. Yes, of course.
But it also shows the virtue of exercises, right? So I mentioned the one that you observed.